right? Now we learned a basic property, which is like the perpendicular from the center to a chord must bisect the chord, and also if a line is drawn from the center to the midpoint of a chord, it must be perpendicular to the chord. Now, as a consequence of the property and its converse, some results that you might want to know out of these. One of course, if we have, so the next few results that I'm going to mention should be looked upon more as corollaries and outcome of this basic result, not as basic theorems though. So let me look at a circle, and let me look at two chords of the circle. Let me look at two chords of the circle, say chord AB and chord CD, and say these two chords are equal in length. Two equal chords of a circle AB equal to CD. Two equal chords of a circle AB equal to CD. Now we want to show that if the two chords are equal, then they must be equidistant from the center. If these two are equal chords, then they must be equidistant from the center, which means, say if O is the center of the circle, let me draw a perpendicular from the center to this chord. Let me call it OP. So obviously if I have drawn a perpendicular from O onto AB, then it must bisect AB, right? That means P must be the midpoint of AB. That's a consequence of the basic theorem on chords that we learned. Also, if I draw a perpendicular from O onto CD, say OQ, then this Q must be the midpoint of CD. The perpendicular from the center to a chord must bisect the chord. So P and Q are not just the feet of the perpendiculars from O onto the two respective chords, but they are also the bisectors of AB and CD. So OP and OQ are respectively perpendicular bisectors of AB and CD. Now let me join these two. Okay, so one thing, AB is CD, so half of AB will be also half of CD, right? Hey, but half of AB is AP. Why so? Because P is the midpoint of AB. So that leads to AP equals half of CD. Half of CD means CQ, right? So AP is equal to CQ. Not only that, AO is the same as CO. AO is the same as CO. So let me call this condition 1. Let me call this condition 2. Why so? Why is AO equal to CO? Because they represent the radii of the same circle. They represent the radii of the same circle. Also, notice that angle APO is the same as angle CQO. Each is 90 degrees, right? That's out of construction. We constructed it like this. Therefore, these two triangles that are observable here, right angle triangles, these are right angle triangles, triangle APO and triangle CQO are right angle triangles, having this side equal to this side and having AP equals CQ. So if two sides of one right angle triangle be equal to two sides of the other right angle triangle, then the two right angle triangles must be congruent. That's out of the RHS condition for congruency. That's out of the RHS condition for congruency. And this obviously would imply that the side OP must be equal to side OQ. Side OP must be equal to side OQ. Side OP equal to side OQ, which means distance of this chord from the center must be equal to distance of this chord from the center. If OQ and OP are equal, the two equal chords must be equidistant from the center. So that's another very important property that we would look at. If we have two chords that are equal in length, if we have two chords that are equal in length, then they must be equidistant from the center. And the converse of this result is also equally good, equally true, equally useful, and equally applicable. Which means, if we have two chords of a circle, and if they are equidistant from the center, then the two chords must be equal. Let's examine that result then. Let's examine the converse of this result. That means two chords equidistant from the center must be equal in lengths. All right. Say this is a circle, center O of the circle, and we have a chord AB like this, and a chord CD like this, say. Let me just draw a better figure so that you know. If this looks any better. AB and CD are two chords, and say the two chords are equidistant from the center. These are two chords equidistant from the center of the circle. AB and CD equidistant from O. O. That means OM must be equal to ON. That is, the distance from O of this chord is OM, must be equal to its distance from O, which is ON. And obviously distance means perpendicular distance of O from this is equal to perpendicular distance O from this chord, right? OM is ON. We want to be able to establish that AB must be equal to CD. The converse of the previous result. Now that's not difficult, because exactly the same way we looked at the situation earlier. Look at this. Look at triangle AMO, which is this triangle, and triangle CNO. Look at this triangle. Look at these two triangles, right? The ones I have shaded. Now in these two triangles, one, AO is CO. Why so? They are radii of the same circle. They are radii of the same circle. All right. These are right angle triangles, by the way. And equidistant from the center O means OM equals ON. OM equals ON. Why so? Because the two chords are equidistant from the center. The two chords are equidistant from the center. That's given. That's given. And therefore, triangle AMO will be congruent to triangle CNO. Why? Out of RHS. Both are right angle triangles. This is 90 degrees. This is 90 degrees. These are right angle triangles. And if two of their sides be equal, then their third side must be equal. The two triangles ought to be congruent. Triangle AMO then would be rendered congruent to triangle ANO. These are congruent triangles. Congruent out of the RHS condition for congruency for right angle triangles. Now if that be the case, very clearly fourth, AM must be equal to CN out of congruency of the two triangles. Now if AM is CN, would you mind believing that AM is actually half of AB? Why is AM half of AB? Please tell me. Why is AM half of AB? AM is half of AB because the perpendicular from the center to a chord bisects the chord. This is a perpendicular from the center to the chord. It must bisect this chord. So AM must be equal to MB. So AM must be half of AB. Exactly the same way. The perpendicular from the center to a chord must bisect the chord. So CN must be equal to ND. That means CN must be half of CD. CN must be half of CD. Right? So if AM is half of CN, then very clearly half of AM, or rather twice AM, must be equal to twice Cn, right? Twice Am is twice Cn. But what's twice Am? AB. What's twice Cn? CD. Twice Am is AB and twice Cn is CD, which means the two chords equidistant from the center must be equal, right? So this then offers a very important result for two equal chords of a circle. If two chords are equal, they must be equidistant from the center. And the converse of that result, if the two chords are equidistant from the center, then they must be equal in length. Very commonly used result, right? Now, what if the two chords are unequal? Which is closer to the center? If we have two unequal chords, which one would be closer to the center is a result that you might want to examine, right? Say if I have a chord like this, and I have another chord like this. O is the center. Say this chord is AB and this chord is CD. And these are their respective perpendiculars from the center. Say this one is at a distance d1 from the center and this one is at a distance d2 from the center. And say this chord is closer to the center. That means, let's say d2 is smaller than d1. That means CD is closer to O compared to AB. Right? So if CD is closer to O compared to AB, that means D2 would be smaller than D1. Now, these two are right angle triangles. This triangle and this triangle, they are right angle triangles. Very easy to see then. And AO and CO both must be equal to the radius r of the circle. AO and CO each equal to the radius r of the circle. Then what is AM? AM is root r squared minus d1 squared. What is CN? CN is going to be root r squared minus d2 squared. Now which is larger, AM or CN? Hey, if d2 is smaller compared to d1, then d2 squared would be smaller compared to d1 squared, isn't it? d2 squared would be smaller compared to d2 squared. d1 squared, d2 squared smaller compared to d1 squared. That means r squared minus d2 squared must be larger than r squared minus d1 squared. So if d2 is smaller compared to d1, then d2 squared would be smaller compared to d1 squared. Then minus d2 squared must be greater compared to minus d1 squared, right? Which means r squared minus d2 squared must be greater than r squared minus d1 squared. Which means CN must be larger than AM. CN larger than AM. But what CN? See, N must be the midpoint of CD. Why so? Because the perpendicular from the center to the chord must bisect the chord. Therefore, CN must be half of CD. And similarly, the perpendicular from the center to a chord must bisect the chord. So, AM must be half of AB. So, which means if I multiply by 2, 2CN greater than 2AM. But what's 2CN? CD. CD greater than AB. Which means what? The chord that is closer to the center is the bigger chord. The chord that is further away from the center is the smaller chord. This is a chord further away from the center. It's a smaller chord. Closer to the center, bigger chord. The closer you get to the center, the greater the size of the chord. And conversely, if we have two unequal chords, if one is known to be larger than the other, then the one that is larger must be closer to the center of the chord compared to the other chord, right? So this brings us to yet another very important result on circles, a corollary of what we have learned. We'll add a little more after a while. This much for this time. Wait for more. Thank you.